All right, section 9.3, the integral and P-series tests. So first, the integral test. If a function is positive, continuous, and decreasing on its interval, and we talked about this in class, we let the terms of the sequence, we let a function mimic the terms of the sequence, then the sum of the series and the integral either both converge or both diverge. Okay, apply the integral test for convergence or divergence of this series. So 3 conditions to use the integral test, and you're told to use this one. Positive. Okay, well, for any positive integer that we plug in for n, all of the terms of the series will be positive. It's continuous on the domain of positive integers. So now we just have to show that the function is decreasing. So let's define f of x as x over x squared plus 1. So now find the derivative, bottom times the derivative of the top, minus top times the derivative of the bottom, all over bottom squared. Okay, so we have x squared plus 1 minus 2x squared. So this would give us negative x squared plus 1. So for any value greater than 1, f prime of x will be negative for any value of x greater than 1, and therefore the third condition is satisfied, that the function is also decreasing. Okay, so then the integral test says, all right, well then let's make this an integral from 1 to infinity of x over x squared plus 1. So now we're bringing in chapter 8. So this is an improper integral, okay? So we will have to replace the boundaries and evaluate the limit, but let's look at a u substitution first. U is x squared plus 1, du is 2x dx. So I need a 1/2 out front. So I have 1/2 times the limit as b approaches infinity of the integral from 1 to b of 1 over u du. So this antiderivative, 1/2, limit as b approaches infinity, ln of u from 1 to b. Sorry, I didn't leave enough room. So 1/2, limit as b approaches infinity of the ln, u is x squared plus 1, minus the natural log of, when I plug 1 in, 1 squared is 1 plus 1 is 2, minus the ln of 2. This limit approaches infinity, therefore the series diverges. Okay, so the limit, if the limit exists, then the improper integral would converge, and therefore the series would converge. Since the limit does not exist when we attempt to evaluate the improper integral, both the series and the integral diverge. Okay, so positive, continuous. I'm going to write this as x squared plus 1 to the negative 1. The derivative, negative 1 over x squared plus 1 squared times 2x. All right, so that's using our power and chain rule. So for any value of x greater than 1, f prime of x will always be negative. And where does the x greater than 1 come from? Our index on the series. All right, so now we can apply the integral test. So I have the antiderivative from 1 to infinity of 1 over x squared plus 1. Attempt to use substitution. U is 2x, doesn't exist in there. This is your arctan. So this would be the limit as b approaches infinity of arctan of x from 1 to b. Okay, so this is the limit as b approaches infinity, arctan of b minus arctan of 1. Okay, if you recall the behavior of the arctan function, as b approaches infinity, this limit approaches pi over 2. Arctan of 1 is pi over 4. Since the antiderivative exists, so since the integral converges, therefore the series converges. So we write a series as an integral. We evaluate the improper integral. If the improper integral has a value, the integral converges, therefore the series has to converge as well. And likewise, if the integral diverges, the series diverges. Okay, when using these tests for convergence and divergence, they show exactly that, convergence or divergence only. The value of the integral is not the sum of the series. So for the previous problem, okay, we got that this series converged. We cannot say that the sum of that series is pi over 4. Okay, next, P series in the harmonic series. So a P series, 1 over n to the p, where p is a positive constant. Okay, the harmonic series is when p is equal to 1. Okay, p is your exponent. So when I look at 1 over n, if I keep adding these, okay, 1 plus 1/2 plus 1/3, this is a specific series, a specific P series. P series is very easy to use for testing convergence and divergence, which I didn't put in there. So, missed that note. Let's add that in there. All right, so your P series test. So we have a P series defined, n is equal to 1 to infinity of 1 over n to the p. Okay, this converges if p is greater than 1. So it converges if your exponent is bigger than 1, and therefore it diverges if p is between 0 and 1, and if p equals 1. So p is a positive constant, so we can only look for values of p greater than 0. The P series diverges if your exponent is between 0 and 1 inclusive. It converges if your exponent is bigger than 1. All right, so apply the P series test. All right, this is a P series with p is equal to 1. Therefore, the series diverges. Done. Okay, P series again. This is a P series with p is equal to 2. Therefore, the series converges. Okay, so you have to make sure you're answering the question that's being asked. Does the series converge or diverge? A very simple test when it's set up as a P series. Okay, let's look at this one. Determine if this series converges or diverges. Okay, so we look at this, and the 1 over n, it looks like it may have some properties of a P series, but we can't use the P series to determine if this converges or diverges. So let's use the integral test. Okay, all my terms are positive. My function is continuous. Now let's look at the derivative. So if I write f of x as x times the ln of x to the -1, okay, my derivative, the derivative of the inside will take the power rule. So product rule. First times the derivative of the second plus second times the derivative of the first. So cleaning this up a little bit, 1 plus ln of x all over x ln of x squared. We can't forget about our negative here. So we can put the negative out front if we want to write it like that. Denominator will always be positive. If I think about distributing this, now remember, it's on the interval for all values x is bigger than 2. So for any value, that should be an x, for any value bigger than 2, your derivative is always negative, and therefore your function is decreasing. Okay, so I can use the integral test. So to set up the integral test, 1 to infinity of 1 over x ln of x. Let's make u the natural log of x. So du is 1 over x dx. So this would become the limit as b approaches infinity, integral of 1 to b of 1 over u du. Okay, the antiderivative of 1 over u is the natural log. So I have the limit as b approaches infinity of the natural log of u, or nope. It's the natural log of u, replacing u with our original ln of x from 2 to b. Okay, so limit as b approaches infinity, natural log of the ln of b. The limit only applies to that, minus the ln of the natural log of 2. Okay, this approaches infinity, and therefore the series, since the antiderivative diverges, I should say the antiderivative doesn't exist. So since the integral diverges, the series diverges as well. I'll see you in class.